All right, so we've talked about measurement, and now we're going to talk about what are called significant figures. So this is part 2 in your notes handout. Um, when we record data, we are creating what are called significant figures. Sometimes we refer to them as sig figs or significant digits. But essentially, if we look at a graduated cylinder, like this example that we already had with our measurement section, we said it was 52.8 milliliters. The question is, how reliable is this number if I'm not also looking at the graduated cylinder itself? So I have to be able to recognize just by looking at a number on a page how reliable the number is. So significant figures, and in this case we have all three of these are considered significant figures. We'll talk about how to determine that in just a second. These are the digits that can be relied upon, especially when we're doing calculations from that data. So if it was important to me that I knew the exact volume of this liquid to the nearest tenth of a milliliter, I could look at this number and know that it was in fact reliable to that decimal place. So what digits are significant? What makes a sig fig? The easiest example are non-zeros. So like in the number 1.38, all three of those would be considered significant figures. Captive zeros, which are just the zeros between non-zeros, are also significant. So in the number 502 seconds, there are also three sig figs because this zero in the middle between the 5 and the 2 is also considered a sig fig because it is captive. Trailing zeros will only be significant if the number contains a decimal. So for example, 7.500 milliliters, those two zeros are considered trailing zeros, and the thing that makes them sig figs is that the number does contain a decimal. So this number would have four significant figures. The 7 and the 5 are non-zeros, and the trailing zeros are significant because of the decimal. Now in this next example, 1,200 kilograms, the zeros are just placeholders. They are not considered significant figures. Okay, so in other words, we can only rely on this number to the nearest 100 kilograms because the sig figs are the 1 and the 2, right? So the last sig fig is in the hundreds place. The other two digits beyond that are just placeholders. Here's another example. Trailing zero, the number does contain a decimal, so this trailing zero is significant along with the 5 and the 1. So this number has three sig figs. We could also say this number is reliable to the nearest 10,000th of a liter because the last sig fig is the 0 in the 10,000th place. These two zeros out in front are leading zeros, or you can just consider them placeholders, a lot like these two zeros. They're just holding the tenths and the ones place, so they are not considered sig figs. And then finally, here's an example where we have a bunch of trailing zeros. It doesn't matter if they're to the left or the right of the decimal. If they are trailing and the number contains a decimal, so in this case we have 200.00, all trailing zeros are significant regardless of where they are relative to the decimal, as long as there is a decimal. Another way of looking at this is thinking of the zeros that are not significant. So all zeros that are just placeholders are not significant. It doesn't mean they're not important in the sense that we can't just erase them. So we wouldn't want to change 1,200 kilograms into 12 kilograms, right? That would change its value by quite a bit. So it is really, really important that we have placeholders, but we should also recognize that this number, for example, would not be reliable to the nearest 1 or even 10 kilograms. So this number could actually be measured more precisely, 1,185 kilograms or 1,206 kilograms, right? So that's why we need to recognize significant figures. Okay, Now we are going to jump past our part 1.1 practice, so you don't have to worry about those. You can take a look at them if you want to, but we will do those in class. And we're going to jump right to part 3 and talk about how to do math with significant figures. In other words, rounding answers to proper sig figs. Okay? And I guess I said that twice. Oops. All right. So the first rule is going to be for multiplication and division. Okay? With multiplication division, the rule says the answer should be rounded to the same number of significant figures as the measured value with the fewest. And don't get confused by measured value. That just means if you were multiplying or dividing a measured value by a counted value, like we talked about in class, finding the average height of students in class, the counted value would not get considered when it comes to significant figures. But usually, all the numbers you put into your calculator, in most cases, are going to be measured values. And so let's take a look at an example. Let's say we were multiplying 20.5 by 18. Okay, so let's just say maybe this is a length and a width, and we're trying to find area in centimeters. The calculator gives me the raw answer 369. Okay, let's think about this. 369 is how many sig figs? So hopefully you realize it's 3 sig figs, right? Because they're all non-zeros. Okay, but the rule says that our answer has to have the same number of significant figures as the measured value, and we're going to assume both of these values here were measured, with the fewest, right? So we have 1, 2, 3 sig figs in 20.5 because that's a captive zero, and we have 2 sig figs in the number 18. So of course 2 would be the fewest. So we can't leave this answer this way because we need it to only have 2 sig figs, right? So how would you round 369 so that it only had 2 sig figs? Okay, and hopefully you said 370, okay? We are going to keep a 0 in the ones place as a placeholder. We don't want to say 37, right? And that's okay because that 0 is just a placeholder because there's no decimal. So 370 would be 2 sig figs, which matches the number 18, which was the part of the problem that had the fewest. Let's take a look at division. Let's say we're finding density of a gas, and we have a mass of 0.8, and we're going to divide it by a volume of 3.05. And the calculator spits out 0.262295 grams per liter. Well, according to our rule, that would be way too many sig figs, right? Because these would all be significant, well, these non-zeros, right? So on top, hopefully you can see we only have 1 sig fig, and on the bottom we have 3. So we are limited by the one that has fewer. Okay, and this might be counterintuitive because you might want to have your answer to be as precise as possible. But remember, this 0.8 grams is only reliable to 1 sig fig. So it could actually be 0.7632 grams or something like that. So we can only rely on 1 sig fig here, which means we can only have 1 sig fig in our answer. So think for a second about what this number would round to expressed to 1 sig fig. Okay, and so hopefully you can see that it would be 0.3 grams per liter, which would be a better answer, even though it looks a lot, or it is a lot less precise. But this actually expresses the precision of my least precise, or the number that went into my calculation that was least precise and had fewest sig figs. Okay, so this is the rule that we follow for multiplication and division, which is what we do most of the time in chemistry. So this is the most important rule when it comes to rounding for significant figures. The other rule, though, that is important, addition and subtraction, we will sometimes do this. This is a little different. We're not counting up sig figs this time. We're going to say the answer should be rounded to be as precise as the least precise measured value. So for example, if we subtract 2,490 minus 26.7, Our raw answer, unrounded, would be 2,463.3. Okay, but this time it's not about counting up sig figs. We have a different rule when we do addition and subtraction. So we're not concerned with how many sig figs, we're concerned with how precise each value is. And what that means is, where is the last sig fig in each number? So in 2,490, the 0 is just a placeholder. So the last sig fig is in the tens place, right? The 9 would be the last sig fig. So this is a number that is only reliable to the nearest 10, okay? The second number has its last sig fig in the tenths place, right? The 7. So our answer needs to be rounded to reflect the least precise number that we used, which was the top number. So our answer needs to also be rounded to the nearest 10. So if we take 2,463.3 and we round it also to the nearest 10, we get 2,460. Okay, let's try one more. If we have 1.50 and to that we add 0.418, we get 1.918 grams. Okay, but we can't leave it quite this way, right? So how precise is the first number? What do we think? Is that 0 significant? Okay, yeah, you should say that this 0 is significant, and it is in the hundredths place. This 8 is the last sig fig in the second number. It's in the thousandths place. So hopefully you can see that the least precise of these two numbers we're adding would be the first one, so the hundredths place, which means that our answer needs to be rounded to the nearest hundredth of a gram. So 1.918 becomes 1.92 grams. So we'll get lots more practice with this going forward, and it's going to allow us to know where to round our answers when we do a calculation in the lab. All right, I'll see you guys next time.